Now we're going to take a look at an application problem. One of the great things about exponential growth and decay is they have lots of real-world uses. You'll use them in science, business, lots of different engineering type of applications. And so we can actually model exponential growth functions, or decay functions in this case as well, with this common formula right here. And we call 1 plus r the growth factor, and of course if it were 1 minus r, that would be the decay factor. And what it'll do is it'll give us a growth rate, if you will. The r will be the rate that we're growing at, or that we're decaying at, and then we're raising it to a value of t, which is expressed in terms of time. The a value, if you recall from the graphing, was our y-intercept and what we would consider our starting point, or our initial given amount in any application problem. And so this is a generic model that we can use for a lot of real-world applications. So go ahead and try to work sample problem 3. It is complex the first time you see something like this, but you can work through it and come back and look at the solutions and fill in the gaps. Alright, for sample problem 3, we go all the way back to the beginning of the internet, or pretty close to back in 1993, and you can see there were only 1.3 million internet sites, which was pretty low amount compared to today's standard. And over the next 5 years, it actually increased 100% per year. Now it wants us to write a model for that. In this case, the model is S in millions after t years. Okay, so basically what we've got here, when it asks us to write a model, we want to use this idea of a growth factor. But when we write a model, we want to write a model that represents the given scenario. So we're actually going to have the number of internet sites, S. We started with an A amount of 1.3 million, so we have to write that in there. We had 1 plus the rate. Now this can get a little tricky. 100% actually goes back to a decimal of 1.0. And so we're going to raise that to a t number of years. So our model looks like this. Now, order of operations says we cannot multiply the 1.3 million times 2 because you have to raise it to the exponent first. So this is our model with the given exponent as a variable. And so that's what an exponential model should look like. Now, we want to know how many host sites were in 1996. Well, if this started in 1993 and we have in the t and then in the number of years, we actually have to figure out how many years that was. And so there has to be a little bit of work done here first. We know that 3 years is going to represent our t in this situation, so we're going to say S equals 1.3 times 2 to the third power. And if you put that into your calculator, just 3 years later, we had over 10 million websites. All right. Now it wants us to graph the model. Now you could simply do this. You could input your t and get your output with the number of S values. And so if you inputted 0, we know that our initial was around 1.3 million. We already did for 3, which is about 10.4 million. If you plugged in, let's say 5, you get to roughly 42 million. Now how do you graph that? Well, I've given you quadrant 1 here because this is only realistic for positive values, and you would have to make up your own scale. And so this is key that you do this correctly. And so you want t for our input values, you want S for our output values. And to graph this, we have to come up with a different scale for each part. And so for the years, I'm just going to simply say 1, 2, 3, 4, 5. But that won't work for the internet sites. So we have to come up with a different model. So I'm going to do it a little differently. So I'm going to say 5, 10, 15, 20, 25, and 30. But this is in millions. And so we get a clear indication. And so if you look, our first point is 0x, roughly a million. And that's telling me in year 1993, we had 1.3 million. 3 years out, we had a little over 10 million. 5 years out, we were a pretty good ways up there. And you can see that that follows my exponential growth model pretty decently. So you're just going to have to get comfortable scaling your own graph there. And then our last question says to use the graph to estimate when there were roughly 30 million internet sites. So we can take 30 million internet sites and kind of work our way backwards. That's a very, very rough estimation, about 4.5 years. And so 4.5 years in would be 1997. And so we'll teach you a more exact way to get that figure in later lessons. One of the reasons I love exponential growth functions so much is because they have so many business applications. In this particular situation, we're going to take the growth factor that we learned about, the model that we learned about in the previous video, and we're going to apply it to interest rates. Now, many of you learned about interest rates, and the only thing you learned was I equals PRT. This is what we call simple interest. And that's equal to the principal, which is the initial amount. Think of that as like your y-intercept, times the rate, the interest rate, times time. Now, the problem with simple interest is simple interest only pays you once a period, and it only pays you the same amount of interest each time period. It does not actually roll over on top of itself. Whenever money interest is added into your balance to calculate the next set of interest, this is actually called compound interest. This is how interest really works in the real world. Very rarely do you get a situation in the real world where you have a simple interest formula or simple interest rate working for you or against you. So you can see here in this little box we have a new formula built off of the growth rate, but this time we've layered in an n value, and that n value is going to show us how many times we're compounding per year. And what that means is how many times the interest is going to be added back into the balance to get a new recalculation. And so this is very important because if over the course of a year, if you put the interest back into the balance and it's recalculated, it's now recalculated on a higher amount, and so you'll earn more interest. That is much better than a simple interest formula. Now, we can simply compound an account in many different ways. We can compound it, once a year, so we could call that annually. We could compound it monthly, semi-annually. We could compound it continuously, actually, but that's a different formula. You can also compound it daily. Now, if we do daily, we're just going to assume a year to be 365 days. And so basically, you can use this formula to figure out how much your money will grow to at various compounding rates. And so you can look here in sample problem number 4. We've given you a bank balance problem that we want you to figure out the balance of the account depending on how it is compounded. And so we can see the differences in the account value that way. So go ahead and try sample problem number 4. Okay, so for sample problem number 4, we'll start with the account balance and we'll do an annual account balance. And so our initial starting amount was $1,000. So we're going to be 1 plus the interest rate, which is going to be 0.08 in a decimal format. Compounded annually, that's 1 time per year raised to n times t. So we're only going to do this for 1 year, and the n is also, the n is also going to be 1 because it's an annual compound. Now, you want to get in the habit of being able to put all of that information into your calculator in one entry line. And if you did, you'll see that our new balance is $1,080. Okay, so let's see how that changes whenever we do this quarterly. Now, quarterly, here, annually, our n was just a simple 1. But quarterly, our n is going to be 4 times per year. So we have 1,000, 1 plus 0.08, and now this time it's over 4, and then we're also multiplying 4 times our t there as well. If you put that in your calculator, you'll end up with $1,082.43. So a little bit more money doing it quarterly. So let's check the daily. So n, and remember we're going to do 365 for daily. And that gives us a final balance of $1,083.28. And so you can see here by compounding more frequently, our balance increases a little bit more because we're putting the interest back onto our account balance more often. All right, we'll discuss this concept a lot more in class so that you get a better understanding of it. Okay, so now we're going to take a look at another word problem. This time you'll notice that we're working with a decreasing percentage, and we will use what's called a decay factor in this case. And so you can see the equality 1 minus r is the decay factor. A lot of times whenever we're talking about a car or a piece of equipment or some sort of asset that a business has, we call this depreciation. So you may see that word from time to time. So go ahead and work sample problem number 5 here and take a look at the solution. Okay, so it says to write an exponential model for the value of the car. Again, we're going to just use the same model we did before, except this time with a decay factor. We had an initial amount of 24,000, now 1 minus the decay factor, 0.16 raised to the t value. As always, you should condense this and not leave it with the operation. And so that is your decay model. Now, it said to see how much the value is estimated to be worth after 2 years. So again, simple plugging in of 2 years for t, and you can see that that value equals 16,934,040 cents. So now we want to graph the model, and of course a simple little t-chart here will help us do this. And again, negatives would be kind of irrelevant at this point for this type of model, and so we will use a quadrant 1 of the graph. And so if I just created a simple input output here, we know that my y-intercept is going to be 24,000. At 2, we were at about 16,900. And I'm just abbreviating here. If you did a few more, you can say 5 and 7 would be roughly 10,000, and then $7,000. And so we would need to do the best scaling that we can as 2. And so we can do years, and then of course we could do in thousands. And so if we graph this, we're going to be somewhere close to 25 at 2. And you can start to see this declining deal, and it would hit that asymptote. It'd kind of start to level off a little bit. So the value of the asset would never actually go fully to 0. You could always scrap the metal of the new car and get some money out of it, so it doesn't actually become worthless at any point. And that's what the asymptote is showing us. Now, part D is asking us to estimate the value of the car being $12,000. So you can see somewhere in here, $12,000 kind of works its way somewhere between year 3 and year 4. So we could simply say about right now, year 3 would be an appropriate response. Now, when we move into logarithms will give us a more exact way to come up with that value, so we don't have to approximate it off of a sketched graph.